The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
Thank you, Van. My talk has to do with basically the engineering side of modulus elasticity. This topic is most particularly affecting tall and super tall buildings. So these are my ideas of what I've seen over the years. Okay. So I'll start with sort of a rhetorical question. Why are we here? Why has this thing become such a hot topic all of a sudden? And the best way that I can describe it is if you think about it historically, going back to the late 60s and early 70s, all the tall and super tall buildings were in the United States, Sears Tower, World Trade Center, John Hancock Center. They were all steel. They were all pretty much office buildings. The Hancock was the one outlier. The slenderness ratio of those buildings was about 7 to 1, maybe 8 to 1. So they were slender, but not so much. Nowadays, you'd be hard pressed to find a single super tall building that's entirely steel. There's a few of them, but for every one of those, there's 50 concrete super tall buildings, and some of them are very slender. Burj Khalifa has a slenderness ratio of 10 to 1. My building in Saudi Arabia, Jeddah Tower, is 12 to 1. There are buildings in New York City that approach 20 to 1. So they're all concrete, and that's how things have developed. It's not that surprising that the issue of modulus elasticity is an important topic for structural engineers. The other way of looking at it is, for us designing these tall buildings, pretty much everything that we do, all of the fancy computer models that we have and all the different platforms, all the permitting that we do, all of the calculations for the tower, including most particularly the wind tunnel testing and the results from the testing in terms of the wind loads and the motions of these tall buildings, all of it has modulus elasticity as one of the variables. All of the vertical shortening calculations that we do for elastic shortening, creep and shrinkage, it's all dependent in some respects on modulus elasticity. So engineers, again, it's not surprising that we would want to put some testing and controls in place for what modulus elasticity our concretes are going to be. Bill Phelan from Euclid Chemical several years ago gave the term athletic concrete. High-strength concrete in these tall and super tall buildings has to do a lot, and engineers should realize that. You can't just specify modulus elasticity. These concretes, they have to have high strength, stiffness, they have to be pumped to very high elevations, they have to be transported to the project site, they have to be placed in the forms, and the concrete consolidated many times around very, very heavy reinforcement ratios. The concrete has to be verifiable. These are very large constructed projects, oftentimes with very thick elements where heat of hydration starts to come into play. All of it has to be done and still have the concrete be economical. So we are asking a lot besides just high modulus elasticity. So our mixed designs can't be just focused on one thing. All right, what does ACI have to say about it all? ACI 318 says you can use 57,000 square root F prime C to do a first estimate for modulus elasticity, and then it goes on to say in the commentary that number may be 120% to 80% of what's going to be actual in the project. So that's a pretty big range for engineers. Could be plus or minus 20%. My committee, ACI 363, High Strength Concrete Committee, says the design engineer would be wise to verify the modulus elasticity based on pre-construction testing and in situ or site testing. All of these are very good things. ACI 363 document also has the infamous scatter plot that I'm sure you've all probably seen that's caused me no end of difficulty around the world on many projects, because it implies, and people have actually stated this, that 57,000 square root F prime C will generally overestimate the modulus elasticity. I don't think that's necessarily true. I think that's a very broad overstatement of the problem. We have to realize that F prime C and modulus elasticity are two very different things and should not be specified in the same manner. One has to do with strength and life safety. Very important. That's codified in ACI 318, what we do with F prime C. Modulus elasticity, not at all, really. Modulus has to do with stiffness and serviceability. Very important topics for the design of tall buildings. In fact, crucial in many aspects, but not specified in the code. The testing requirements are different. Both are standard cylinders, 6x12 and 4x8 cylinders perhaps, but the testing is totally different. The age that we need these things are different. We do not need a target modulus elasticity at 28 days, I can assure you of that. The modulus is there for the long-term behavior of the building over its entire lifetime. So it can be specified at much later dates if it's convenient for the design team and the owner and the contractor. And then the risk assigned. Let me put it to you this way. We over-design mixes for strength. If I want 12,000 psi F prime C, that mix should be reaching 13.5 or 14 on a regular basis. If we tried to do that approach for modulus elasticity, it'd be a disaster. We can't afford to over-design mixes for MOE. We just don't have those kind of margins in the mix designs. So a whole different approach has to be taken. What should engineers be thinking about when they do this? All engineers should know what the implications are if the modulus is a little bit lower than what they thought it was going to be. That's our job. If you say it's 57,000 square root F prime C, we should know what happens if it's 10 or 15% less. Pre-construction testing is a must. To take risk out of the job, you have to do pre-construction testing. You shouldn't start the job and not have any idea whether you're going to hit your modulus under the construction conditions. So that's rule number one in my case. We should know what the conditions are where we're designing our project. Concrete is local, so we should know what can be achieved. We should not be specifying things that just cannot be achieved by the ready-mix suppliers and the contractors. That's where the conversation has to start. And the taller you get and the more slender, the more possibility you're going to be doing a very novel mix at some point that's never been done before. So you got to do the pre-construction testing to know what modulus you're end up with. We have to specify what testing is needed, and we have to be very clear about whether the tests are part of the acceptance criteria for the concrete. We know that contractors, they know, and they're risk adverse, that if they have low strength concrete in the job, it's a big problem. Modulus right now is in a bit of a gray area that needs to get resolved in the engineering and specification community. Again, we need to know what happens if for whatever reason you don't reach the modulus elasticity that you thought you were going to get when you were designing the structure. As you get more and more slender, the issue of stiffness can actually affect the wind loads that are predicted for the building. That's why it's such a critical issue for structural engineers. So there's a feedback effect. But when we do the wind tunnel testing, we do basically a range on many properties, not just stiffness. But stiffness is one of the things that we say, what if its stiffness is 10% less or 10% higher? We do the same thing with damping and other structural characteristics. So we know the answers to those questions before the issue ever comes up on site. Just a little bit of history, because I think it's important to kind of understand where we were and where we came. One of the first projects that in the literature that started to address the issue of MOE for tall buildings was 2 Union Square. It was finished in 1989. Not that tall, it's just 720 feet, still a very significant project. They specified the 19,000 psi concrete, and at least from the literature, the idea was that by doing that, they would sort of back into a target modulus elasticity that they needed for the stiffness of the tower. So that was sort of one of the first attempts at trying to get at this issue of what's the modulus elasticity for that particular project. And then I was involved in one of the two projects you see here in the late 90s. Afterwards, the 7 South Dearborn project, while at Skidmore, Owings and Merrill, 2,000-foot tall proposal. And a little bit earlier, Thornton Tomasetti had the Miglin-Beitler proposal, which was also 2,000 feet tall. You can see these are very, very slender buildings, over 10-to-1 aspect ratio, very, very different from the previous steel buildings. Neither one of them got built, but while we were working on these projects, we started having conversations with Prairie Material Sales in Chicago, most particularly Mike Pistilli, who was a leader of what could be achieved. So we had several meetings about what we can specify, because our approach as engineers was not, we need this. It was more like, what can you give us? And that's the way we should be approaching specifying modulus on these projects. We have to work with the ready-mix suppliers. So at that time, average compressive strengths around 14 or 15,000 psi. Maybe we could achieve a modulus of 6,700 KSI. That was sort of the state of the art in the late 90s as a possibility. And we talked about even higher strength moduluses, what it would take to get to 7,000 KSI modulus back then. And the thought is you'd be specifying strengths probably around 16,000, maybe even higher. And at that point, the talk was that you may have to import aggregate from Wisconsin. The trap rock aggregate up there is much stiffer. That's the coarse aggregate's a very key driver for the modulus, eventual modulus on these projects. So again, these were setting the ground rules for what could be achieved commercially on these projects. And then finally, Trump Tower came along, which was my project. We specified 12,000 PSI concrete at 90 days. After the wind tunnel test, we were actually able to reduce the modulus elasticity requirement to 6,200. That's exactly 57,000 square root F prime C. So as far as I know, this was the first super tall building in the United States that anyone had directly specified a modulus elasticity value for that project. The MOE for Trump, we had several pre-construction meetings, and Prairie Material Sales very quickly latched on to the idea, so is this going to be an acceptance criteria for the concrete? And my answer was, no, we're not going to treat this like strength, but if we continue at some point to routinely miss our target modulus elasticity, we're going to change the mix design. So we had done some pre-construction testing, so we were pretty well assured that we were going to hit the target reasonably for that particular project, and that was an important aspect of it. For that particular project, because you can imagine if you specify MOE, you're going to get a lot more cylinders to have to test. So we did do correlation cylinders between static and dynamic testing. Seems like that's gone a little bit out of favor in Chicago, but it's still an option to be able to make it a little bit more efficient in terms of the number of cylinders tested. That was a very successful project. For the 12,000 PSI concrete, we were probably on average at 90 days, we were around 13,700. We didn't have many issues really at all in low strength concrete on Trump Tower. It was a very successful project from that standpoint, with very good, very small standard deviation in my opinion. And the modulus, the target there is the horizontal line. We were able to achieve at 90 days without too much difficulty. Again, we didn't really have any episodes of low modulus concrete on the project really whatsoever. As part of that project, we had 3 areas of the project, special areas where we had outrigger walls and belt walls, very highly stressed elements located at the mechanical floors. And for those, we specified 16,000 PSI concrete. And we worked with Prairie Material again to do pre-construction testing on those. We didn't really need the modulus for those because you can imagine it's only 2 stories at 3 locations. So the modulus really was not that important. but we were able to achieve something on the order of 7,300 KSI. And the reason that's important, at least in Chicago, there's a history of taking concrete one step at a time, project by project. So if we can use the technology for a project, do some testing, pour a column or two with high strength concrete, and then use it on the next project as a test, that's what the industry should be doing, rather than starting from scratch all the time. So we keep building in Chicago, project after project, year after year, decade after decade. And finally, that 16,000 PSI concrete, in a very similar fashion, the idea was to use it on the Chicago Spire project, another 2,000 foot tall building that actually the foundations are all in. And the idea was to use higher strength, high modulus concrete for that very slender proposal in Chicago. Just recently, one Bennet Park topped out in Chicago. It's about a 900 foot tall residential building, again very slender in one direction. We specified basically the same specification as Trump. Testing was done in pre-construction, but also at the base of the tower. The first few floors, 7, 28, 56, and 90-day testing for modulus, and then every few levels just to make sure that we weren't somehow, dropping below our targets. Again, MOE was not discussed as an acceptance criteria, but again, enough testing was done that we knew that we were going to be able to achieve it. This isn't a particularly high modulus for 12,000 PSI concrete. It's only when you get up to, I would say, closer to 7,000 KSI is when it becomes a little bit more problematical, at least in the city of Chicago. For Jetta Tower, believe it or not, the high strength concrete that we specified there was 12,500 PSI. Again, we asked for 6,300 KSI, and it's been a struggle, believe it or not, and that has to do with the quality of the coarse aggregate there. So again, we specified it. That one we're quite strict in terms of the modulus and the amount of testing to make sure that we're getting very close to the requirement. But here's what's happening with the strength. So our 85 megapascal concrete, 12,500 PSI concrete, is routinely testing out at about 115 megapascal. So it's 85 megapascal in name only. It's really a higher strength concrete than that. And you can see the strength gain here. We're testing all the way up to 180 days and even 365 days, honestly. But we have no problem whatsoever with strength. And here's modulus. We asked for 43 gigapascal, and we're getting about 42 at 180 days, and we're having more tests at 365 days. But you can see it flattens out very quickly. The horizontal line is age. So if you look at the previous slide, there's strength, there's modulus. Modulus reaches its peak pretty quickly, and then you don't get a whole lot of gain over time, at least for this mix in this particular part of the world. Again, I'll say it again, all concrete is local. May not be true elsewhere. So that one, we had to get much higher strength concrete to be able to do it. And of course, this concrete needs to get pumped up to 600 meters in elevation and then pumped again up to the top of a 1 kilometer tall tower. So modulus is only one of several things that the contractor and the supplier has to deal with. So anyway, I hope that it gives you an idea of what we do as engineers on some of these tall projects, super tall projects. And one thing I'll just very quickly mention. We have buildings on the drawing tables even today that are much taller than the ones that have been built. And they're in various places around the world, a few of them in Chicago that will be taller than anything that will be there today. So the issue of modulus elasticity is not going to go away. It's here to stay. It's only going to increase, and the need to have mixes that can reach target modulus is extremely important for us as engineers of tall and super tall buildings. It's something that it's not that new. It's been going on now for probably 30 years in inexact form. And it's one of the things why we're so pleased to work with our final speaker today on some research that hopefully can has a potential to maybe tackle this in a little bit different way. And we've been involved in those discussions, and we'll continue to do that. And we hope that as the years go by, we'll continue to have the right ideas and the right way to specify this for everybody, not just the structural engineers, not just for the building owners, but also for the contractors and the ready-mix suppliers that are key elements of the building team. Thank you.
Okay, thank you very much, Bob. We have time for a couple of questions. Okay.
Oh, I guess the question was, is there a risk with high modulus that the concrete becomes brittle? No, I don't think any more brittle than all the rest of the concretes. I don't think it's a particular issue at all. The ACI 318 does not have a limit on the strength or modulus at all. Actually, it applies to all high-strength concretes.
Okay, one more question. Okay, hearing none. Bob, thank you so much. Yeah.
My pleasure.